Okay, today we'll continue with the slope deflection method. So we can see the problem sheet here that we've got here. So these first two are the simpler problems. There's not much to this one here. It's the same idea as before. So if you imagine you've got a cantilever beam just moving your way in from this side here, then you would probably be able to say that the bending moment diagram is going to look something like that, triangular going along there. So you don't need to calculate that using the slope deflection method. So it's 100 times 3, which would be 300 kilonewton meters, and then we would put that arrow there, and then we'll put that arrow on that side there. So that would be 300 kilonewton meters, and because they're going upwards like that, I'll put hogging. So 300 kilonewton meters, and then if you wanted to call this MB looking towards C, so you would put MBC, make sure that MBC is clockwise, which it is, and so MBC would be equal to 300 kilonewton meters clockwise. And then on the other side here, when you do the slope deflection, we'll be trying to work out whether it's positive or negative, positive being clockwise and negative being anti-clockwise. So we would draw all the arrows on this side here in the clockwise direction. So we would put that as MBA, and then we will call that one in that direction there, and we'll call that MBC, which is also acting in the clockwise direction. So when we calculate these out, if either turn out to be negative, then that will define whether the other one is whether it's hogging or sagging. And then here we'll just say MA is equal to 0. So if you go onto the Dropbox, you'll find a full solution for that. So this 0 here denotes MA. This 75 there would denote MB, which would turn out to be 75 kilonewton meters sagging after you've done the calculation. So after you've done the calculation, you'll find that MBC is indeed anti-clockwise, and MBA should be, MBC is clockwise and MBA should be anti-clockwise. So MBA should come out to be negative. And then up here we've got that one as hogging, and this one here as that one here as MC. So MC, the bending moment at C, is going to be 300 kilonewton meters hogging, and we can see that the arrows here would be in the hogging direction. So that's the thing that you need to resolve before you do the calculation. And of course here right at the end of the cantilever, MD is going to be 0, which is what you would expect. So full solution on the Dropbox, and the answers are, it's up to you to interpret if they're sagging or hogging. So that would come out in the wash, meaning that when you do the calculation, MBA would be negative or anti-clockwise. So this is after you've done the calculation, and then MBC would be positive, which would be clockwise. Okay, and then from there, once you've got that, then you would be able to work out the reactions of the statically indeterminate structure. And actually this one here, technically speaking, these should be pin and roller, and then this one here would be statically indeterminate by 1, since if you remove that one, it would be statically determinate. So this is the one unknown, so statically indeterminate times 1 or by 1. This one here, similar problem to what we've seen before. So when you do the slope deflection calculation, first thing to do is to put everything in as clockwise. So you would be putting in the arrows here because in the clockwise direction, because you don't know what they are, and you would be using the slope deflection method to help you calculate it. So everything drawn in the clockwise direction, and you would be able to deduce that MD would be equal to 0. So the bending moment diagram would probably look something like that. And then, so we sort of covered this before. So this one would turn out to be sagging. So when you do the slope deflection equation, that would turn out to be negative, and that would turn out to be positive. They're both clockwise at the moment, so it's negative, so it'll be pointing in that direction. So that would relate to that value, and I presume that that value there would relate to that value there. Okay. So when you do the calculation, it might say what is the active bending moment diagram. So the active bending moment diagram for AB is, so that would be the active bending moment diagram for AB, and the active bending moment diagram for BC, which I'll draw a bit lower, would be 0 because there's no load acting on BC, and the active bending moment diagram acting on CD would also be 0 because there's no load on it. So for the active bending moment diagram, just pin simply supported on the span that you're after with the load applied and work out the bending moment diagram. So this would turn out, for the active bending moment, that would turn out to be 50 kilonewton meters, and then 50 times 50, so that value there would turn out to be 2000 kilonewton meters, I would hope. Okay, so these are the basic problems. Now let's turn the page. So here we've got an advanced problem, which is a portal frame. So the first thing that I would say, the first thing that I would note is that this is a sway frame. So it's that means that it's not restrained from swaying, but in this particular case, because the load is symmetrical, the frame is not going to sway. So we can use the slope deflection equation for this particular case to calculate what the bending moment diagram would be. Now, for example, if we took exactly the same problem and we had the load on half the side, then this one here would be swaying. So I'll go through it later. So that would be a sway frame, and I could call this a no sway frame by symmetry. So you can solve sway frames using the slope deflection equation, but we've not talked about that. But later on, we'll be talking about other methods, such as the flexibility method, which you can, and also virtual work, which are other methods which would enable you to be able to draw the to calculate the bending moment diagram of sway and non-sway frames. So just take a quick look at this one here. So I'll take that one out for the time being, and I'll take this one out for the time being. So what we're saying here, so firstly these are fixed, so you can see it's got these pegs that go in. So these two ends here are fixed. This one isn't fixed, so you can see it's smooth at the end, so that means it can happily float around here, and that can float around here. So so we should all know that when we draw that, we would draw that with the hashes to show it's fixed. So sometimes some confusion can happen because you might think that this or the joints of a frame, where you show the joints, they're actually fixed in space and fixed in rotation, which we can clearly see. In this case, it's not. So when you've got a frame like this one here, now we can see that this frame can sway. So you can see that the frame can sway over here. So incidentally, when we looked at the slope deflection equations, we removed the last bits, which were the deltas. If you go back to that equation, that would be the sway, okay? So that would be the sway. So you can see that the frame is able to sway on either side. Okay, so let's just put it up here. Now, as I said, if you put the load there, there would be a tendency for the frame to want to sway to that side. And if you put the load here, there would be a tendency for the frame to want to sway to the right side. So as soon as the load is asymmetrical, the frame would have a tendency to sway to the left or to the right. But if the load was put right at the center, then by symmetry it's not going to sway to the left or right, if you can see that. So I've applied the load and you can't see it swaying to the left or the right, so it's not swaying, as you can see there. So we'll just leave it there. You can see that as this load comes down, these things here rotate, so there's a rotation at the joints, but you would be able to see that before you put the load on, it was at 90 degrees, so that member and that member are at 90 degrees. And when I release the load, that's 90 degrees. When I apply the load, it's 90 degrees. So 90 degrees to each other. So you can see from here that the joint, so maybe these would be welded together, or they would be forming a joint, and the joint would maintain that 90-degree angle. So this is certainly not fixed in space. Okay, so sometimes when students see joints, they think that the joint is actually fixed in. Let me see if I can demonstrate that. So sometimes when students see that, they might think that they might see the joints as being one of these. So they might see the joint as being a fix. Okay, so if it's a fix, fixed in space like there, and also I've got another one here. So sometimes the misconception is that the joint fixes the joint. The joint is fixed in space. So you can see if both sides were fixed, then you just got fixed end moments, and both loads would be going to just any load that was applied here would just be absorbed. So I can't get this in. Give me a second. Yeah, so it's certainly not fixed, because if the load was going in there and that was a fix, then no load would be transferred back and there. So let me take that out. So it's clearly joints are clearly not fixed, and we'll put the joint back there here so that you guys can see it again. Sorry, just bear with me on this one here. So now when it comes, so I hope that in place there. So you could hopefully sort of see that if the load was bang on in the center, which is what I'm trying to illustrate here, there is a rotation, and it's almost as if this beam is being supported by the column. Okay, so it's almost as if the beam was being supported by the column. So just for the case of that one there, if I turn that into one of these here. So I'm now, so in this case here, when these were there was clearly no support, and now here I'm pretending there is some support to the, sorry, let me just get this in. So there's a bit of friction in this, which is not ideal, but hopefully you can see that, you know, when I apply that, these columns are almost applying that vertical restraint there, and still around there it's allowed to rotate around. Okay, so that brings us to how we solve this actual problem. So it could be demonstrated by maybe, so I take that out to start with. Oops. And maybe there might be enough space here, so sorry, having to improvise since we're in lockdown. So instead of that, it could be like that. So remember, this one was the middle span with the UDL acting on it, and technically speaking, we should have not one of these, but one of these which would allow the lateral movement, not lateral, sorry, allow it to slide. So technically so we, oops. So if I apply the load there and allow that one to move in, then you can probably, so that would have been the column, that would have been the right hand side column, which would have been down there. That would have been the left hand side column going down there, and we can see that it's almost the same. So that's a good enough approximation for how that portal frame can be analyzed. So let's apply. I'll pretend we apply the load there as a UDL, and you can see the deformed shape. So you'll be able to see that this one here is hogging. I'm going. This is hogging down here, and this would be hogging down here. Okay. So let's see how that would work out in the sketch. So we'll just get rid of that for the time being. So we'll go back to the page. Go back to the page here. And so we've got a frame. This frame can sway, as we said, but if the load is symmetrical, it could be like that, and we would be able to say that would be AB, put B on the roller, and then BC, and then CD. So we would say we could imagine that we would be able to, that you can solve this problem here, that being A, that being B, that being C, and then that being D. So under this, the bending moment diagram could be expected to look like that, and to look like that. And hopefully by the end of the problem, after you solve the slope deflection for that one there, you would get a bending moment diagram that would hopefully look something like that, and then going on that side there. So both sides would be symmetrical, and everything else is the same. So here at the end of the calculation, you would get that MBC in this direction as shown, which would be clockwise, and the other side would be MCD, and that one would have to be anti-clockwise. Okay, and it would be exactly the same here. At the end of the calculation, you would get that, and at the end of the calculation, you would deduce that that arrow is in that direction. So as we said, this is on the outside, so the bending moment can't switch. So the outside would put that as the tension side, and so on the column side, that also has to be the tension side. So the tension sides cannot switch without an external moment being applied. And if we look to move that one there, so that one would look like that. So that would be your MCB, same as that one in the same direction, and that one, the CD would be in that direction after the calculation, so that obviously will turn out to be negative when you use the sign convention, but you can see that and that are in the same direction, and then that and that. Okay, and then just to finalize things, I suppose you could put that one there. So that one would be on that side going there, which would be the same as the reaction solution. So again, on the Dropbox, you would find a full work solution for this one here, and then you would be working out these key values, 55, 1, 1, 9, 1, 3, 8, 3, 9. Okay, and remember that's a line of symmetry. So it is a sway frame, but you can say it doesn't sway because of symmetry of the load, and for that reason we can do what we've done here, and it's exactly the same whether you solve that problem or this problem using the slope deflection method. And then the last problem, so there's this thing here, well, technically speaking that should be on the roller, but because of this, the frame has suddenly become non-sway. So if going back to this one, this is a sway frame, but if you suddenly put a prop here, then the sway frame becomes a no sway frame. Right? So with a prop, that stops the sway, which is what this is meant to be doing here, stopping the sway. So you can do exactly the same trick. So you would have A, B, C, imagining that C is being supported by that column D, and then down here you would have the D going down there. So that would be A, B, C, and D, and then you've got the load there. So as the UDL. So that's part of one of the problems with that you'll be dealing with in this case here. And the other problem relates to the fact that this is 2, this is 3, and this is 5. So this is the bending stiffness. So the bending stiffness of each member is not the same. So if we look at the first equation, it would be MAB minus M fixed AB, and that's going to be equal to 2 times bending stiffness. So in this case here, the bending stiffness is 5 EI. Remember, the EIs will all cancel out anyway. So if you really wanted to, you could just substitute a different value for the EIs. So EI over L, and L in this case is here, and then it would be 2 theta A plus theta B, etc., etc. So for this problem, as I said, there are full solutions on the Dropbox, which you can have a look at, and just make sure that you can do these under examination conditions, and just remember the problem of the sway frame, or the no sway frame, and of course any sway frame can be turned into no sway just by sticking a prop on that would prevent sway, just by pinning that point. So that's the end of the slope deflection part of the course. So by this stage you should be able to get 1/3 of the marks in the exam, because the first question would relate to slope deflection and drawing bending moment diagrams, things like that. If you flick over here, plenty of examples and plenty of solutions in the Dropbox that you can go through, and just make sure that you can do these. There are not too many tricks that can be used. So by the time you've done a few of them, they should all be quite straightforward. And what's important is to be able to do it reasonably fast and without making any error in the algebra. So these would be the final exam questions from previous years relating to the slope deflection method, and I would probably have you probably finished it in about 30 minutes, 35 minutes for each one of these. Okay. So I've got a solution for the 2017 exam question, which you can see here. But as I said, there are solutions available in the Dropbox for these. Okay. So before we finish this, just go back to the front of the course book. Now for the solution of simultaneous equations, so in the exam we would obviously expect you to provide enough workings so that you can be sure, you've just not copied the answer from somewhere. But one bit of software is the online beam frame analyzer, in which you can set up almost every single problem that we've got here. And in terms of the simultaneous equations which we're solving with the slope deflection method, there is a simultaneous equation solver that some students have identified for me in the past, and you can use that to solve the simultaneous equations, or just make sure that what you've worked out when you solve the simultaneous equations for the slope deflection method does work out properly. So those are two things that you can use to check stuff. Okay. So now let's move on to the next section of the course. So the next section of the course is going to be dealing with bending. Sorry, not bending. It's going to be dealing with buckling of compression members. So let's have a look here. So here I've got a beam, and this end is on the roller, and the other end I will be putting on a pin. So I will put this in here on a pin. So pin and roller. So we've got that down here. Okay, and these are actually columns. Okay, so why don't we just turn it around here so you might be able to see it as a column. Okay, so the section's called buckling of compression members. So we'll just have a look at it from the model there. So here we've got a column. So one end is beam, one end is pinned, and the other end is roller. So I think I'll just for argument's sake, I'll turn it around like that. So if I'm going to be showing it as a column. So if it was a beam, it would be taking, lateral forces or moments. What happens with columns? So I'll turn it around as a column. There's not too much friction there. There's a bit of friction. Okay. So with a column, when I stick a load down here, you can suddenly see. Oops. So yeah. Okay. So that's due to the lack of, needs a bit of grease. Okay. So when I stick a load there, this is what's known as an instability, and the instability is called buckling. So I'm sticking an axial force down there, and suddenly it springs out. Yeah? So you can see it there, and that's called buckling. So before we go any further, it's not the same as bending. Bending is when you've got a lateral force coming in that direction there. So buckling is not the same as bending, and we'll just have a look at some of the subtleties of the equations later on. But what I would be trying to show is that a column will not be able to take more than the buckling load. So I'm not able to compress this without it buckling. So suddenly you see it buckling like that. So I'm not able to put a force on without it suddenly shooting out sideways. Now with bending, if I stuck a load down there, it will go in that direction, and if I stuck the opposite load, it will go in that direction up there. Okay. Now if it was a column, as you can see here, I can apply a tension force in that direction, so I can shove a force upwards at this end here, and it's not becoming unstable, and it would just elongate with the axial stiffness Young's modulus times the cross-sectional area of this thing here. But when I stick a load down in the opposite direction, it becomes unstable. So here I'm putting a small load on, and you can see even with a small load on, the thing would want to come, it wants to buckle outwards. Okay, so even with a small load, it would want to buckle outwards. So let's make some observations. So I'll push that down there. Okay, so I'll push that down there as it buckles. So the first thing that you might be able to observe is that that's a sinusoidal function. So you can see that it's a sinusoidal function. So the buckling instability is a sinusoidal functions. So we're going to be seeing a lot of sines and cosines in some of this. Now, if I applied the load down like there, you can see it buckling. So free rotation here, and also free rotation here on this side here. And in terms of the length of the sine wave, so that's a half sine wave length, which we can see there. Okay, so we can see that's called 1/2 sine wave, and it buckles with a length L, or whatever the length of the column is, over that half sine wave. Now if I change this guy here from a pin, so at the bottom of a multi-story building you might have a fixed column base, and if I did that, you can see it's a different shape. This one here used to be, when it was a pin, it was rotating around, and you can see that now is coming out at 90 degrees. So you could sort of deduce that's also a sine function, a sinusoidal function, but the length of the buckle is not from here to here. So if we look at the deformed shape here, we could probably see the buckle could be from that point there, or the length of the half sine wave could be from there to there. Okay, so that's not quite clear, but we'll see that later on. Okay, so and that's with a change of the boundary conditions. So let's have a look at buckling of compression members. So so as I think I showed in the demonstration, it's going to behave differently whether it goes into tension. If it goes into tension, there's no buckling. There's only buckling if it goes into compression, which I've shown there, and then it can buckle in 1/2 sine wave. So which way it goes, whether it buckles to the left or whether it buckles to the right, actually makes no difference at all. The way it would choose to buckle based on some impurities in the material or something that makes it more susceptible to go to one side or the other. But it really makes no difference at all when it comes to the mathematics. And as I mentioned, we call that a half sine wave, buckling over the length L, because that would be the length of the beam or length of the column L. So L would become your half sine wave. Without wanting to jump too far, there's going to be a load that we can calculate at which the column will buckle, and that load is known as the Euler load, and the Euler load, or PL, will show in the proof, is pi squared EI over L squared. So if we applied pi squared EI over L squared, pi squared EI over L squared to a column, that is the elastic critical buckling load, or the Euler load is just one of the few things that structural engineers need to remember. And a column cannot carry more than the elastic critical buckling load pi squared EI over L squared, because once it buckles, deflections, stresses, everything shoots off to infinity. So it's sort of the upper bound as to what a column can carry. And the other thing that I would mention is when you use your calculator, remember, because we're talking about sinusoidal functions, remember to set your calculator to radians, okay, and don't use degrees. So before we start, let's have a look here. So if you look in the Dropbox, which we've got there, we've got buckling of compression members, and I've got solutions for the in-class problems, the tutorial problems, and the class test and the exams. I found something written out here by this guy called Degree Tutors, so you can have a look at that file if you wanted to. We'll be having a look at one example later on, which would be in 1. So I'll just say that here I've got a video demonstrating using the 3D printed kit different buckles. So if I pause that one there, you can see that having a restraint in the center, which is what that is, having a restraint in the center, and you can see that it buckles into 2 half sine waves. Okay, so it buckles into 2 half sine waves and it behaves the same as that one there. So I've got a video here which you can have a look at if you wanted to, and it's in the Dropbox, and I called it 3D printed parts demonstration of buckling. Okay, so let's now have a look at the material. Everything here in the course book has been taken from the textbook Mexen. So if you got Mexen, if you got the Mexen textbook, then this is simply just simply Mexen. You could have a look at some of this stuff here. So some stuff in Wikipedia, concept of free body diagrams, and as we've said, everything's almost been taken from the Mexen textbook, structure and stress analysis. If you're looking for a different textbook, the Gear and Timoshenko textbook, Mechanics of Materials, is also particularly good. So here we'll have a look at the table of contents and the sort of things which we'll be covering. So Euler, pi squared EI over L squared, so the Euler buckling is going to lead us to pi squared EI over L squared. For pin-entered columns, which is the one that I've just shown, so the pin-entered column would be looking like that, with the load coming down like that. And then what happens when we change the boundary conditions? What happens, or how do we handle it as engineers if the boundary condition becomes a fixed? Okay. And the way we handle it is this effective length. So this is pin, and then if that was, say, 1 meter, we would say the effective length to use here, that's really our effective. The effective length to use in Euler is 1, and if it was this case here, then it might buckle like that, and the effective length may be a bit shorter than 1. So we'll be using a different value, and we'll be showing from the mathematics how to get that different value. And then we'll be talking about in terms of slenderness. Later on, we'll be talking about the design standards. So the New Zealand design standards, like most of the other standards for buckling, it would use the Perry-Robertson formula. So, and basically, you know, there's no such thing as a perfect column. This is all very idealized and very elastic, but in reality, some columns would be imperfect. They wouldn't be perfectly straight. They might even have a small half sine wave, a very small imperfection in them. They may not be straight. The support conditions may not be exactly accurate. You may be sticking your load on at a small eccentricity. So all of these things can be covered in the real world using test data, and then that's mapped onto what's known as the Perry-Robertson equation. So we'll be covering that. So introduction to buckling. So you can read that, but I hope I've demonstrated it, and you can also get a feel as to what buckling is, just with a simple ruler, and just apply some compression onto that ruler, and you will see that it suddenly buckles or suddenly becomes unstable. So buckling is an instability, and I've already demonstrated what happens when you reverse the direction and put it to tension. There's no instability, and if it goes in tension, it would fail. It would be presumably to fail by the material. Okay. So that's your pin case, and that's buckling into 1/2 sine wave. So if you remember, sine waves or cosine waves would look like that. Okay. So this is 1/2 sine wave from there to there, and that would also be 1/2 sine wave, because the sine wave, as you know, goes around up to 2 pi. Okay, and that would be pi. So the buckling it would buckle into 1/2 sine wave, as you can see there. So Euler buckling theory for slender columns. Slender just means something that's going to want to buckle, and Euler theory is going to lead to P Euler pi squared EI over L effective squared, which would be the equation that you need to work out. So pin-ended columns, we'll start by exploring the mechanics. So we've got a column like there, one end pinned, one end roller with the force coming down here. So I would probably have preferred to see that like that, but never mind. I think you all know what that means. So the key word is, well, this is theoretical. So theoretically, the column is perfectly straight. Theoretically, the column is uniform, and it's got perfect pin-ended, so perfect friction at the two. Sorry, not perfect friction. Perfect frictionless supports at the end that would allow the rotation, and it's of length L, which is shown here. We assume that the column satisfies the Euler-Bernoulli theorem. Plane sections remain plane, and also obeys Hooke's law, so it's linear elastic. The column is homogeneous. The column's Young's modulus is E. Incidentally, another thing to remember for E is, I think it's 210 times 10 to the 3 newtons per millimeter squared for steel. So it's somewhere between 200 and 210 for steel or the metal. And the cross-sectional second moment of area is I. So if you remember, if you've got something like that, and that is buckling over that axis, then it will be 1/12 times BD cubed. So just remember, when we looked at the previous, when we looked at the prerequisites to this course and in the basic skills thing, you do need to have a recap as to what the second moment of second moment of area is, or the moment of inertia. Now we're saying the axial force is aligned perfectly with the longitudinal centroid of the column. So that's not something that can be done in the real world, but in this artificial world, we're assuming that the line of action goes right through that line there. So in the real world, with defects, with the way that people make connections, it could be like a couple of millimeters out, and that P could be either to the left or to the right. But for this case here, we're assuming that it's aligned perfectly. So the trivial case is when the column remains straight. So remember, if the column had been in tension, like there, it would have remained straight, and it would just have extended by something related to the EA, where A is the cross-sectional area. So the trivial case is that the column just compresses. So in the same way that if that was the column, perfectly straight column being pulled apart, you might be able to see that it's extended by that bit there. And if the same column had been compressed, then it may just have got a bit shorter. Yeah, it would just have been compressed. And so the trivial case is when the column remains straight and just becomes a bit shorter. However, we know from the observation of what I've just shown with the stuff that it might buckle, i.e. lose its straight configuration. Assume then that the column has lateral deflection V of x. So that's the lateral deflection V of x taken at an arbitrary point. So that probably relates to something like there. So assume that it has a lateral deflection and its equilibrium in this configuration. So here we see the load P. The column has buckled. The P is now being applied with an eccentricity of Vx, and as you know, there will be a bending moment on either side of the cut, which is, so I don't want to call it hogging or sagging in this case. We just say that there's a bending moment, and that bending moment is mx, where m is a function of x going along there. So if you remember the equation, a bending moment is equal to curvature, which is d2v by dx squared, multiplied by EI. Doesn't really matter about the minus. So we would go back and examine that expression, and to calculate the bending moment at an arbitrary point from the bottom, we've seen figure 3. Take moments, P is an eccentricity as I've just described, and we ignore the influence of structural deformations on the internal forces. In buckling, we do consider structures in the deformed configurations, and so the moment equilibrium relationship reads as the bending moment mx is equal to P times V of x. So that should be quite obvious from here, that m of x is P times that distance there on the buckled shape. So if we substitute that relationship back into equation 1, we get this expression here, which is a linear homogeneous differential equation, which I'm sure you've covered in year 1, and that's got constant coefficients. To simplify it, introduce alpha squared equals P over EI as a parameter, and then you get that expression there. And then using the Trowel solution Vx e to the Rx and substituting back into there, we get 2 roots, with one of which is imaginary. Therefore, equation 4 has the real solution. V of x is equal to a sine alpha x. So at this stage here, of course, go through the maths that you've done in the first year. But secondly, and more importantly, is the physical interpretation. And remember that when we looked at the column when we looked at the column, I don't think it was this one here, but this one's not bad. Let's put this down there. When we looked at the column and we applied, no, that's not what it should be. Okay, let me take this one out here. So we take that there, and this one here still isn't. So unfortunately with lockdown I can't go back to my office and get my books and everything, and I don't have a printer at home, and I don't have the rest of this kit here. So I just try and make do with what I have. So again, sorry if these lectures seem to be taking too long. So, so this one here, is more frictionless than this one. This one was a bit tight, so this one needs a bit of grease. But that's an example of imperfections in support conditions. So I'm now going to stick it into compression, and I hope you guys can see that. Maybe I'll move it over here. That might be a bit clearer, so you can see it. And the important thing is that you can observe, even just by looking at it, I would hope that the buckled shape is a half sine wave. So that basically means you sort of knew the answer before we started, that the V of x, which is the shape here, the V of x is going to be a half sine wave, okay, and which it is for the buckled shape. So V of x is a sine alpha x plus b cosine alpha x, And now let's stick in the boundary conditions, and I'm sure the boundary conditions will tell us that b is 0, that b is 0. So we now need to consider the boundary conditions for the pin, which means v, which would be that or that, is going to be 0 at here and at here. And substitution of the boundary conditions into equation 5 means the only possibility is that b is equal to 0. So by inspection of the 3D printer kit, we could have predicted that v of x is going to be a sine alpha x. So substitution leads a sine alpha x. So remember, there was a trivial solution. So the trivial solution is the inverse of the tension, or the opposite of the tension solution, whether it's an extension or a compression and no buckling, which is very, very hard for a very slender member to show. So there are two solutions. One of them is a equals 0, and this corresponds to the trivial solution. The trivial solution being, if I'm not going to stick a load on, but if we just imagine I stuck a really small load on, this is just going to compress in the axial direction, and so there's going to be no v of x is going to be 0, v of x is going to be 0, and the beam remains straight. However, there are also non-trivial solutions, i.e. non-zero solutions. And the non-zero solutions is sine alpha L is equal to 0. So alpha L is equal to n times pi, and n is equal to 1, 2, 3, 4, 5, and up to infinity. And since alpha squared is going to be equal to p over ei, the above condition is satisfied only when the axial load p takes on the specific or critical cases given by that equation there. And it would take on the lowest one, which is an n of 1. To each critical load corresponds a particular buckled shape, which we can see here. So n is equal to 1, which is 1/2 sine wave, n equals 2, 2/2 sine waves, and n equals 3, 3/2 sine waves, as you can see there. So here we stick this on here, and we can see that it buckles into 1/2 sine wave. Now, what happens if that was a column, that was a beam, so this is a column, and this is maybe a beam coming into the column providing some lateral restraint, which I'll show by pushing it, and we can see that it buckles into 2/2 sine waves. So it would tend to buckle into the lowest mode, which would be the 1, but if there was something there, then we do have enough for a solution. So in other words, if there had been a support, if there had been a restraint at that position, which I could show either using my finger, or let's just say if there had been a restraint or support there. I know that this one isn't halfway down, but it does demonstrate that there is a support that could be anywhere, and you push it here. Oops. Maybe I'm not going to be able to demonstrate it on this. Part of my problem is that I can't see very clearly. These things a bit fiddly. Okay. So I've got it. Oops, no, I haven't got it in. So you can see that it would buckle like that. Okay, and if this one had been dead on in the center, which I've not shown, then as my finger indicated just now, if it was dead on half, oops, if it was right at the center, or at half length of the beam, then you would have your 2 half sine waves. And if it was 3, I wouldn't be able to show that, but if it was 3, maybe it would be 3 half sine waves. Okay, so it's always gonna buckle into the lowest mode, and unless there's a restraint at that position, then it's just going to be n of 1. So to each critical load corresponds a particular solution, which is a sine n pi x over L. And in practice, unless we restrain the column during the loading, it's going to buckle with n is 1, as I've just demonstrated, or taking on the value of the half sine shape a sine pi x over L. So in other words, when I apply my axial force in compression to a column, it's going to buckle like that. And if I said that that's my axis V and that's my axis X, so you want when X equals L for that position here to be 0, which is what this expression would be. So when X is equal to L, so when X is equal to 0, that function is there. When X is equal to L, it's sine of pi, and sine of pi is 0, so that corresponds to there. And then A would be the amplitude. So that equation does seem to work out. So from now on, we're referring to the critical load unless otherwise stated. We'll assume that we mean the lowest value of 1, subscript 1, or PCR, which is why we've got the 1 there. And then this table here summarizes the values of the critical loads for columns with different support conditions. So at the start, I said we've got a load there being applied here over that effective length there. And that one is pi squared EI over L squared. Okay, which is the Euler, and that was what I wrote to remember up here. Pi squared EI, technically speaking, L effective squared. Pi squared EI L effective squared. So we can see where that equation comes from. What happens when we've got different boundary conditions? If both ends were fixed, so that's pin, pin, so that's pin, pin. If it was now fix, fix, we can see that PCR has gone up by a factor of 4 in comparison to the pin, pin case. So having both ends fixed increases the value by 4. This one here is a cantilever coming down, and it's not 4, it's 1 over 4. So you can remember the cantilevered case compared to that one there. It's a quarter of that value. And these are two other conditions: fix with sway to one side, and this one is pin and allowing the sway to one side. So this one here turns out to be the same, pi squared EI over L squared, which we can see there. And then this one here turns out to be 0.25. So what we'll be doing now is we'll just be having a look at maybe that one there, which is the 2.05, and we will have a look at that in this example 1. So if you go back to here, I'll show you what there is. Firstly, last year or some time ago, I've got a solution where I wrote out the solution for this. Which you can see there, and you can see me talking to some graph paper and also some text, which we can see there to solve that. So this is the critical load in the bucket shape of a column with one end fixed and the other end like that. So I've got a video there, and some of you don't want to watch the video, I can understand that. It just takes up too much time and you just want to look at a written answer. So there's a written answer here for this case here, all right, which you can have a look at, and then how it solves it through the graphs, okay, and then gets that value of 2.05. I've got another solution. I've got a solution that I dictated before, which is on the YouTube links. So that one is down here if you wanted it. My PhD student Arthur has also written out a solution, and he's also got a video that goes through the solution of this problem there. So if you need any help, you can contact him if you need any help on that email address there. But he's got a video and he's also got a solution. Okay. So, and up here you saw some graphs, and if you click here, you'd be able to see the graphs that I had a look at for the solution of this one here. So at the end of the day, we work out an equation to tan alpha x, and we have to read off where the two lines meet. So I'll talk a bit more about this one tomorrow in tomorrow's lecture, but for now, if you wanted to skip ahead, there's plenty of different alternative ways of looking at the solution, and possibly, if you even wanted to, the Degree Tutor's Guide for Buckling would give you a solution for that. Okay, so that's it for today, and I'll talk about this one again tomorrow.